Welcome to Visual Algebra Lecture 3.6, Conjugate subgroups. In this lecture, we will continue to study conjugacy classes of subgroups. We'll start by learning about unicorn subgroups. And yes, that definition is new to my video series and book. This will help us identify normal subgroups by inspection, just from the subgroup lattice. We will prove some basic algebraic results about conjugate subgroups, and then explore how to find them and what they look like in a Cayley graph. Let's get started. Often, we can determine the normal subgroups and, more generally, the conjugacy classes of subgroups. Remember, the normal subgroups are those of size 1, simply from inspecting the subgroup lattice. We will make frequent use of the following straightforward result in this lecture and beyond. This says that a subgroup H of order 2 is normal if and only if it is contained in the center. So in other words, if and only if both elements in it commute with everything. Let's prove this. So an if and only if means that we have to prove both directions. So we'll start with the backwards direction. And this one is almost immediate. If a subgroup is contained in the center, then it has to be normal. So let's just write that down. So all subgroups in Z of G are normal. Remember why that is? Let me do it up here. So if H is central, that means Hx is equal to a set of all products of the form H little x. And if the elements commute, then we can write this, and that's by definition the right coset, Hx. So we always have that. Let's do the forward direction. So let's suppose that H has order 2. Oh, and I should say, just to emphasize, this condition is not H as order 2, it's H is normal, and the other condition is it is contained in the center. So the subgroup of order 2, that's just an assumption. Let H be normal in G, and say that H consists of two elements, one being the identity and the other being some other element H. Let's compare left and right cosets of, or let's say, take any x in G. Our goal is to show that these elements both commute with, well, just that H commutes with x. We already know that the identity does. So let's compare left cosets. XH is x times the two elements E and H, which is the two elements x and xh. And then the right coset, hx, is E comma h, that two element set, times x on the right, which is x and hx. Now, these two cosets have to be equal because h is normal in G. Well, obviously, x and x are the same element, but that forces these two elements to be the same. In other words, xh equals hx, and since x was an arbitrary element in H, that means that H is contained in the center of G, and that's what we wanted to prove. Consider a group G. I'll use D4 for an illustrative example, and suppose that we conjugate it by some unknown element x. Let's compare the subgroup lattices of G and the subgroup lattices of its conjugate. Conjugating G is going to conjugate all of the internal subgroups, and so this might shuffle around the subgroups of a certain order. Here's one thing I want you to notice. There are 5 subgroups of order 2, and one of them just looks differently than the rest. This one here, it's got 3 parents. It has order 2, order 4 subgroups that contain it, and the others don't. So when we conjugate these subgroups, look over here, you can see right away which subgroup has to be that one. It's the one with 3 parents. In other words, x r squared x inverse equals r squared for all x in G. So because this is at a unique lattice neighborhood, it has to be normal. And I call this thing a unicorn. Now I could formalize this as being lattice automorphism invariant, but I don't even need to do that. I just want to be able to look at a subgroup lattice and say, hey, this subgroup looks different than the rest, therefore it has to be normal. And for that, the term unicorn suffices. Now, the full group and the trivial group are always unicorns. Therefore, they're always normal. These 3 subgroups have index 2. They have to be normal. What else can we say? Let's take the subgroup generated by F. This has order 2. We know that F is not central. It does not commute with R. So therefore, we proved in the previous slide that this cannot be normal. So it has to have some other subgroup conjugate to it. I like to call it a conjugate buddy. Now you could check that F is conjugate to R squared F. You could just check that RF, R inverse equals R squared F, but I'm going to show you how to do that just by inspection. This subgroup up here is normal, which means when we conjugate it, all of the elements in there just get shuffled. In particular, these 3 subgroups, they can never get sent outside of there because this is normal. So this thing has to get sent to, well, it can't get sent by conjugation to the identity, but it can get sent to possibly one of these 2 things. Well, that one's central, it can't, but this subgroup has to be conjugate to something else. And there's only 3 order 2 subgroups that are inside here. So it has to get conjugate, or has to be conjugate to that one. Because again, it's in conjugacy class of size bigger than 1 because it's not normal. And this is the only bachelor inside of here. Similarly, these 2 things have to be conjugate over here. So we just determined all of the conjugacy classes of this group by inspection from the subgroup lattice without doing any calculation. We didn't have to check that RF, R inverse equals R squared F or anything like that. I used without proof, just appealing to your intuition that conjugating a normal subgroup by some unknown element will shuffle its elements and subgroups within it. But we should probably prove this. Formally, if n is normal in G and H is contained in n, then every conjugate of H is contained in n as well. Let's prove this. And notice that I didn't leave much space. So if we conjugate H by some arbitrary element in G, what do we get? We get H, or XH, X inverse, is contained in XN, X inverse. So if I conjugate both sides of this by X, I get that. But what is that if N is normal? That's equal to N. And that's exactly what I wanted to prove. So again, H is contained in N. We conjugate both. This thing doesn't move, so every conjugate has to be inside this. Here's a picture of part of that previous subgroup lattice. So from the previous slide, this is the subgroup generated by R squared and F. This was normal. And this is the center. We said this was normal. And then conjugating this subgroup, we said because this is non-central and order 2, it's got to have another conjugate buddy. That one's out of commission because it's central. So it's got to be conjugate to this. In other words, if we conjugate everything here by some unknown element x, here's what we have. And if x is the identity, then all of these are going to be unchanged. But there is something that we can conjugate this thing by to make it equal to that. Let's really quickly recap what we learned about this group and its conjugacy classes just by inspection. Let's quickly recap what we've learned about this group from the theory we've developed just by inspection. First of all unicorns, oh, by the way, I've colored the unicorns purple, as they should be, and index 2 subgroups are normal. We said that the subgroup generated by F cannot be normal because it's not central and order 2, so it has some other conjugate. However, each conjugate of this subgroup must be contained in the normal subgroup that contains it, so there's only one other possible conjugate buddy, because this one is normal. Therefore, the conjugacy class containing this subgroup has size 2. It's these two subgroups. We can even, by inspection, find the normalizer of this subgroup. Remember, the index of the normalizer is equal to the size of its conjugacy class, so that must be index 2, and there's only one subgroup that contains it of index 2, so this must be the normalizer in G of the subgroup generated by F. Similarly, this is the normalizer of the subgroup generated by R squared F, and the normalizer of these two non-normal order 2 subgroups is the index 2 subgroup that contains it. In summary, we just determined all conjugacy classes of subgroups and all of the normalizers simply by inspection. I think that's pretty cool. We've developed some really powerful theory. As I mentioned earlier, our definition of a unicorn could be strengthened, but we want to keep things simple. And let me just ask you this thought experiment. This is the subgroup lattice of the diquaternion group, DQ8. Remember, this is what we get by taking the quaternion group and adding in a reflection matrix. There are 4 C4 subgroups. Are any of them unicorns? Are any of them not like the others? Well, upon first glance, they all have 3 parents, that is, subgroups of order 8 that contain them. So they look like they're the same. But if you look more carefully, you'll see that one of these subgroups here is contained or has 3 parents that are all C4 cross C2. Whereas these 3 are all contained in a quaternion, a dihedral, and an abelian subgroup. So this subgroup right here is actually the subgroup generated by I0, 0, So this is a scalar of the identity matrix. And this subgroup has order 4. It contains plus or minus the identity and plus or minus I times the identity. And that's central. That's actually the center of this group. So I would say that this is a unicorn because it's different from anytime we conjugate these subgroups, this thing has to go to another C4 subgroup that has 3 abelian parents, and it's the only one that has that property. So even without knowing that this was the center, we could say that this was a unicorn and therefore normal. That's why I don't like, formally define this as automorphism invariant, because you have to keep track of things like the labels. Let me finish by asking you, what can we say about the conjugacy classes of all the subgroups in here just from the lattice? Well, this is something that we will be able to answer in the next chapter. At this point, we don't have the isomorphism theorems to help us, but we can say something. We, of course, know that these 2 subgroups are normal. They always are. This is a unicorn. It's the only C2 subgroup that has 7 parents. That has to be normal. All of the index 2 subgroups have to be normal. And then all of these subgroups here, these are not contained in the center. So all of these are non-normal. So they have to be in size at least, or 2, or a conjugacy class of size at least 2. And let me just show you something. So if you look at this part of the subgroup lattice, if you chop off the subgroup lattice here, and let me draw this little picture. You've seen this subgroup lattice before. Do you recognize it? This is Z2 cross Z2 cross Z2. And one of the powerful results that we'll see in the next chapter is that if we want to get the conjugacy classes of this entire group, what we can do is chop off the subgroup lattice here, take a quotient, and look at the conjugacy classes of that quotient. And this quotient is abelian. So all of these subgroups are normal in the quotient. And by something called the correspondence theorem, they're going to be normal in the big group as well. So with that little bit of knowledge that these subgroups are normal, now we can look at this C2 subgroup and say, well, this has to be conjugate to something else because it's a non-central order 2 subgroup. And anything that's conjugate to has to be inside of this normal subgroup. And well, that one's normal, so that's out of commission. So this has to be conjugate to that. So we know these have to be conjugate, those have to be conjugate, and those have to be conjugate. Then in terms of normalizers, well, all normal subgroups, the normalizer is G. And then these things here, the normalizer of this has to have index 2, because that's the size of the conjugacy class. So the normalizer of one of these things, well, it is either, let's see, it's either going to be D4, this D4, that D4, or C4 cross C2. And at this point, I don't think we have enough to determine which one it is. We just know that the normalizer of each of these subgroups is going to have index 2. However, the moral is that we can say a lot just from the theory that we developed using inspection. And once we develop more theory, like the correspondence theorem in chapter 4, we can say even more than that. Here's a fun exercise. We're going to repeat the process of what we did earlier of conjugating every subgroup in a lattice, but this time for a mystery group that we'll call G. So here's the subgroup lattice of a group of order 16. And let's think about what the conjugacy classes are. So the unicorns are all purple. This is the only order 8 subgroup that has 3 siblings. Well, it's the only non-cyclic order 8 subgroup. This is the only order 4 subgroup with 3 parents. This is the only order 4 subgroup that has 1 parent and 1 child. And this is the only V4 order 4 subgroup, i.e. one that has 3 children. So these are all have to be normal. And this one too, because this is the only order 2 subgroup that has 3 parents. So all of these have to be normal, and also the index 2 subgroups are normal. So that leaves us with just these 2 subgroups right here. And there are 2 possibilities. One of them is that both of these subgroups are normal and in their own conjugacy class. So let me write that down. The subgroup generated by S and the subgroup generated by R to the 4S are normal in G. And if that's the case, well, if this is normal, then it has order 2 and therefore must be central. So if S is central, that means it commutes with R, and that means this entire group is abelian. So that means that S must be central and G is abelian. So I'm not saying that this is even possible, but if this is normal, then this group has to be abelian. Of course, case 2 is that this subgroup is not normal in G, and therefore the other one cannot be normal either. Why is that? Well, because if the subgroup generated by S is not normal, that means it must be in a size 2 conjugacy class. And there's only one other bachelor. It's unaccounted for, so these things have to be conjugate. So that means that the conjugacy class of G containing subgroup generated by S has size 2. It's just the subgroup generated by S and the subgroup generated by R to the 4th S. And this is going to force G to be non-abelian because this subgroup cannot be central by what we proved in one of the first few slides. So it does not commute with everything, so G has to be non-abelian. Now, I'm not necessarily saying that both of these are actually possible. Maybe neither is possible. Maybe this is a made-up, well, you know me too well to know that I would give you a fake lattice here. This is the subgroup lattice of at least one group of order 16. And at this point, I encourage you to think about what this is. I'm going to show you in the next 2 slides, but it's fun to take a guess or try to figure it out first. Okay, here's the answer. It is straightforward to check that the subgroup lattice we saw is that of the abelian group C8 cross C2, which is generated by R and S, where R has order 8, S has order 2. Well, technically, we can just say that R to the 8 and X squared is equal to 1. It takes a little more work to show that these don't have order less than that. And SRS equals R. So if S has order 2, then S inverse equals S. So what this is really saying is that SR equals R S inverse, which is RS. Here's a Cayley graph, and you can take R to be the element A comma 1 and S to be 1 comma B. I'm going to just write these multiplicative, and I think that's easier than these ordered pairs. And I'll let you check that this is the subgroup lattice of this group. So that's our answer. All done, right? Not so fast. The non-abelian case is possible as well. And this is the subgroup lattice of the semiabelian group SA8. Now this is also generated by an element R of order 8 and an element S of order 2, but now we have this other relation. If you have not watched my lecture on semidihedral and semiabelian groups, please do so. And let me just say a couple things. So again, we know that in this case, the conjugacy classes, these are all normal, and these two have to be conjugate. But if you did watch that lecture, you saw that this group and the one that we saw on the previous slide, which was C8 cross C2, had the same cycle graph. I'm trying to remember what it looked like. It was something like, so it had this big 8 cycle. Is that 8? 1, 2, 3, 4, 5, 6, 7, 8. Yep. And then it also had this another 8 cycle that looked like this. And then it had 4 elements of order 2. So let's say I have 8 elements here, 9, 10, 11, 12, 13, 14, 15, 16. Yeah, so both of these groups had the exact same cycle graph, which means that they have the same orbit structure. And in this case, not always, that's enough to force the subgroup lattices to be the same. So this is the smallest example of 2 groups of the same order that are non-isomorphic that have the same subgroup lattice. I bet most people taking and even teaching algebra don't know this example, and it's something that I think they should. And my hypothesis for why most algebra instructors do not know this is because I did not know this until about 2019, after I started writing my book, which you may remember is about 3 years after I first recorded my initial visual group theory YouTube series. Thus far in this chapter, we've come to understand how to compare the left coset GH with the right coset HG, both algebraically and in a Cayley graph. However, to understand H versus this conjugate subgroup GHG inverse, we need to actually compare 2 different cosets, the left coset GH and the right coset HG inverse. And maybe you can see why that's reasonable to expect, because you can see GH embedded in here and HG1 overlapping as well. But there's more to it than just that. Let's prove a basic proposition. If we have the equality of left cosets AH and BH, then we must have the equality of the right cosets H A inverse and H B inverse. I should mention that we need not have the equality of the right cosets H A and H B. So that need not hold, and it's pretty easy to find an example. I think just pick two left cosets that are the same, and very likely these right cosets are not going to be the same. So here's a picture of what this is. Now recall that if we have equality of two cosets, say AH and BH, that just means that A and B are in the same left coset. So over here, we have a left coset AH, which also contains B. So suppose that AH and BH and CH are all the same. We have this equality. And this is the partition by left cosets. And the partition by right cosets, it could leave A and B in different right cosets. So this box up here is HA. This box down here might be HB. And then maybe A inverse is over here, and B inverse is over here, and C inverse is over here. What this is saying is that if these elements were in the same left coset, then their inverses must be in the same right coset. But we don't know about what right coset the actual elements are in. Let's prove this. Shorter than you might think. And this is one that can be a little bit scary because you look at this and you're like not really sure what to do. But fortunately, we don't have very much to work with. First of all, let's recall that I call this the boring but useful coset lemma. An element x is in H if and only if xh is equal to H. And of course, this also holds for right cosets. So we can say this is equal to hx. So these are equivalent conditions. So we're going to use that. It may not be clear how, but we're trying to prove this implication. So let's assume that AH and BH are the same. Okay, so suppose that AH is equal to BH. What can we say? Well, that is equivalent to B inverse AH being equal to H. We just left multiply by B inverse, right? And now we can use this boring but useful coset lemma applied to this particular element. And that's the same thing as saying B inverse A is in H. And that's the same thing as saying H B inverse A equals H. Again, by that boring but useful coset lemma, this element is in H if and only if this right coset is equal to H. And now we're almost done. Now we just right multiply by A inverse. So we just say this is H B inverse equals H A inverse. And that's it. That's what we had to prove. And there's nothing too deep about this. I like to say we followed our nose. Maybe we didn't see how this was going to go, but we wrote down the assumption and just did some algebra. We played with it. We moved the B inverse over. We recognized that, hey, this is a direct application of this indeed boring but useful coset lemma. We just showed that if we have the equality of the left cosets AH and BH, then we have the equality of the right cosets HA inverse and HB inverse. As a corollary, if we have the same equality of left cosets, then we also have the equality of the conjugate subgroups AH A inverse and BH B inverse. To prove this, well, there's not much we can do. We have to assume that we have equality of AH and BH. Then by the proposition in the previous slide, we have the equality of H A inverse and H B inverse. So maybe we don't see exactly how to go, but I say it's like skiing in fog. You kind of point your skis downhill, and you know you'll get there if you're not going too fast and not off course. So what do? We're trying to show the equality here. Let's start with A inverse. And let's write this as A H times A inverse. And by this equality up here, I can write this as B H A inverse. How do you see what we're doing? I can write this as, so I can change the parentheses and write this as H A inverse. And I can write this as B H B inverse, again by this equality. And that's exactly what I want, B H B inverse. And that's it. We got to the bottom of the hill by just pointing downhill and following our nose. As a corollary, if we have any subgroup H of G of finite index, then the number of cosets of H, that's the index, that's an upper bound for how many conjugates there are of H. Now, we actually know a stronger statement, and something that we've proven earlier is that the actual number of conjugates is equal to the index not of H, but of the normalizer of H. So in other words, if we have H here and G here, and this has index n, well, the normalizer is going to have, the index of the normalizer is going to be smaller or no more than n. And so this is the actual number of conjugates. So of course, n, the index of H, is an upper bound for that. These things could be the same, or this could be strictly bigger. So even though we know a stronger result, I'm just going to mention that this result here almost immediately implies that this is an upper bound. Do you see why? This says that for every left so if we can ask how many conjugates do we have of a subgroup? Potentially every single group element will give you a different conjugate, but this says no. Elements in the same coset will give you the same conjugate. Again, we actually know more. We know elements not just in the same coset, but the normalizer of H, that is all of the blue cosets, will give the same conjugate element. I'm going to finish this lecture by exploring how to identify conjugate subgroups in a Cayley graph. And I will use the example of a group that I don't think we've seen before. This is the semi-direct product of C4 with C4. Okay, so to identify the conjugate subgroup GHG inverse in the Cayley graph, let's do the following. As before, we're going to read from left to right. And I'm going to break this up by, first of all, identifying the left coset GH. And then, from each node in GH, follow the G inverse path. Let's do an example. So again, this is a Cayley graph of C4, semi-direct product C4. We secretly know in advance that this first term is, this first subgroup is normal. That's A, and the second one is not. But let's pretend we don't know that and go exploring. So A is a subgroup generated by little a, so it's these four elements. And let's compute BA, B inverse. So BA is left coset by starting at B, doing all the A paths. We're right here. And then let's do the B inverse path from each of these nodes. So that's backwards blue. So from this coset, we do backwards blue. And that brings us back to where we started. So again, BA backwards blue gets us back here. Let's also check that these other conjugates, b squared ab minus 2 and b cubed ab minus 3, are also equal to a. So if we go, so this first one is b squared a, that's this coset right there. And then b minus 2 is backwards blue, backwards blue. So from each of these nodes, following two backwards blue arrows takes us back to where we started. So indeed, we end up back at a. And then finally, b cubed a, b minus 3. So b cubed a, this first one here, that is this coset. And then let's follow b minus 3, which is just the forward blue arrow from each of these, and that takes us back to where we started, which is the subgroup A. So by the previous slide, to find all conjugate subgroups of H, we don't need to check 16 conjugates. We only need to check 4, one for each coset. If you remember a couple lectures ago, we actually don't need to check. We only need to check one for each, the normalizer of each H. But let's stick with this for now. So we conjugated this by one element in each left coset, so that's the identity, b squared, and b cubed, and in all cases, we got a, so we conclude that a is a normal subgroup, which is something that we knew because it's a property of semidirect products. Let's now carry out the same steps, but with the non-normal subgroup, big B, generated by little b, and here is that subgroup right here. So there's two steps, and the first one is to identify the left coset, GH, and so that first step is actually in this picture, and the second step is in this picture. And what we want to do here is I want to find A, B, A inverse. But I added this so I could show you how the right coset and left coset are different. So remember, BA is what we get from starting from B and following the A arrows, which is the red arrow. So this is A, and A. So notice that is different than the left coset, AB, which is starting from A, following all the blue arrows. So the first step, we identify this left coset, and then from each node, we traverse in this case, the A inverse path. So A is red, so A inverse means follow backwards red. So backwards red leads us here. Backwards red from here leads us over there. Backwards red from here leads us back here. And backwards red from here leads us here. And here are those 4 elements that we get. That is a subgroup. Notice this is a subgroup generated by A squared B. So starting from here, red, red, blue, red, red, blue, red, red, blue, red, red, blue. It follows immediately that B is not normal. Of course, we knew that because the left coset and the right coset are different. But let's now find all conjugate subgroups. And remember from what we learned a couple slides ago, we don't need to conjugate B by all 16 elements. We just need to conjugate by one element in each coset, each left coset. And here are those left cosets. So we will conjugate we don't need to conjugate by the identity. We get B itself. Well, we'll conjugate by, if you can see this is dark enough, by all powers of A. We just did one of them. If we conjugate by A squared, so let's do that. We start with the left coset A squared B. Here it is. And then we follow the A inverse path from that. That's the second step. So A inverse is backwards red, backwards red. So from here, we get back to E here. Backwards red, B, backwards red, and backwards red, backwards red. So we actually, in this case, this conjugate of B is B itself. And finally, if we conjugate by A cubed, we start with the left coset A cubed B, and then we follow the A minus 3 arrow. So that's actually the forward, backwards 3 reds is the same as forward 1. So we follow the forward 1 arrow from each of these. And look what we get. We get the subgroup, as we did in the previous slide, generated by A squared B. So it's generated by this red, red, blue element. And that is not equal to B. So there are two conjugates of B, and those are the following subgroups that we've seen. And one's this one and one's that one. And it follows that the index of the normalizer of B is 2. Remember, that's the size of the conjugacy class. In other words, the normalizer has order 8. By inspection, we know what the normalizer is. The normalizer of B are the two left cosets that are also right cosets. One of them is B, and the other one is this coset, A squared B. We can check that this is also, so B, if we do B and then do red, red, we get to those same nodes. But we also know if we take a coset of what we've shown in this lecture is that if we take a coset of B and we conjugate by any element in it, and we get back B, then that left coset is equal to a right coset. So in other words, we know from this lecture, but also from what we proved earlier, that every coset of the normalizer will conjugate B to the same place. So the elements in the normalizer will conjugate B to one subgroup, and in this case, the other two cosets will conjugate B to the other subgroup. I can't end this lecture without showing you the subgroup lattice of semi-direct product of C4 with itself, and here it is alongside the subgroup. Notice that I'm just labeling the subgroups by isomorphism type, and I always leave as homework in my class a problem that involves the following steps. First of all, redraw this subgroup lattice, but label the subgroups with generators instead of isomorphism type. Also, determine the conjugacy classes of the subgroups, and construct a cycle graph. Now, let me say a word about the conjugacy classes of the subgroups. We haven't done the isomorphism theorems yet, but I want you to notice that these three order 2 subgroups are normal because they're all unicorns. This one has 5 parents, this one has 1, this one has 3. So because these are order 2 subgroups that are normal, they are central. So let's circle these. These are size 1 conjugacy classes. So these 3 order 2 elements, or all these subgroups have the identity with an order 2 element, which is central. And therefore, this V4 has to be central as well, because the 4 elements in this V4 are the non-identity elements in here with the identity. So this actually has to be central. One thing that we'll learn later is that the center can't be too big. So we'll understand why this center can't ever have index 2. But we're getting ahead of ourselves. So this has to be normal. And I also want to point out what happens if you take the quotient by these 3 subgroups. And again, this is isomorphism theorem stuff in chapter 4, but I've hinted at, basically told you that if you look at the subgroup lattices above a normal subgroup, you will recognize you're going to get the subgroup lattice of the quotient. And what do you see? So hopefully you recognize this middle one as, this is that kite, which is Q8. This one here, I don't know if you recognize, it's a subgroup of lattice of D4 folded into itself. You see that? It's these 5 subgroups of order 2. Normally these 2 things are sticking out over here. Or actually, normally this one of these is, and this one's in the middle, and these 2 subgroups are swapped, and then these 2 things are sticking out over here. But then finally over here, I need to pick a different color. Let's do green. This subgroup lattice, this is also one of order 8. You recognize that? Getting a little bit crowded here, but that is C4 cross C2. So this subgroup, or this group, is going to have 3 quotients that are non-isomorphic order 8 subgroups. So I actually have a really nice set of exercises involving this subgroup lattice and exploring quotients and doing other things and conjugacy classes. And I encourage you to check it out. It's on my website. It's, I think, like homework 5 or 6, one of those things. But also, I also hinted at that the conjugacy classes of the original group are inherited by the conjugacy classes of the quotient. So this subgroup lattice here is of an abelian group, which means that all of the subgroups are normal. This is the quaternion group. All of this quotient, all its subgroups are normal. Well, so they're all in size 1 conjugacy classes. This is D4. Its conjugacy classes are all size 1, except we saw earlier there's 2 pairs of non-normal subgroups that are conjugate. So from this, and again, we don't really know this until we do the isomorphism theorems, we can determine by inspection the conjugacy classes of all of these subgroups and also the normalizer of all these as well. The normalizer of these non-normal subgroups have to have index 2 because that's the size of their conjugacy class. Okay, so that's a lot of information and a lot of previews that we haven't really established yet involving quotients. But speaking of quotients, quotients are the topic of the next lecture. So we will finally formalize what a quotient is. It's basically collapsing a group by cosets of some subgroup, but that subgroup has to be normal, and we'll understand why that is. We'll also look at products of subgroups. So quotient is a way to divide a group by a subgroup, and a product of 2 subgroups is a way to kind of multiply 2 subgroups together. Well, that'll be a lot of fun. Stay with us.